Hello, my name is Jonathan Lewis, and today I will be presenting my final project for CSE 574. Today we'll be going over two papers, three states in a plan, the AI F.E.A.R, and playing a strategy game with knowledge-based reinforcement learning. Let's start with paper one, the three states in a plan, the AI F.E.A.R. Monolith wanted to create an action-packed experience with AI enemies that mimicked playing against real players. They wanted to create AI that planned around the actions of a player and interacted with the environment in intelligent ways. They only had one programmer to create this complex system, and the problem with this is traditionally methods for creating complex AI require a lot of work, and for one person to do this, it would be very difficult. They were able to achieve this using only a finite state machine with three states, which utilized planning. Why is it difficult to implement complex AI? Traditionally, AI was created using a star for pathfinding and a finite state machine to control the actions that can be taken by the AI. Some of the main challenges for creating complex AI come from transitions within finite state machines. Complex AI require a large number of states that fluently transition between each other based on the scenario. The more complex the system is, the more you need to manage these transitions to prevent the system from breaking or performing an action at the moment. These transitions need to be implemented into the code by a programmer and can take quite a bit of time. Adding a new state into these systems can later in development can be challenging because you want to make sure that your new state transitions do not interfere with previous transitions. F.E.A.R approached this in a very interesting way by utilizing planning to dictate when the AI should transition between states. So, as previously mentioned, the team utilized a finite state machine, which only required three states, which is very different from previous implementations. The three states used are go-to, which has the AI move from one location to another, animate, which plays animations such as shoot, reload, or idle, as well as the last state is use smart object, which allows the AI to interact with smart objects within the environment. So this can be activating a switch or flipping a table to create cover. A-star was used to plan sequences of actions, which control the actions taken by the state machine. So the system that they do does have some strong resemblances to strips. So the system that they use is a goal-oriented action planner. Each AI needs to be assigned a goal set in order for it to function within the level. Actions taken by the AI include preconditions, which need to be met for an action to be taken. F.E.A.R uses a progressive state-based planning similar to strips. The AI planner will work to satisfy the highest priority goals similar to strips. If there are multiple goals, similar to strips, if there are multiple goals that need to be met, the planner must choose which goal needs to be met first. Each character has their own action set to achieve goals from the goal state. Plans within F.E.A.R sequences of actions to achieve these goals. These plans are short and often under 4 to 5 actions in length at their highest, but normally only consist of maybe 2 to 3 actions. Here's an example of how a goal set can be utilized for 3 different characters. This goal set consists of 2 goals, patrol and kill enemy. So here within our first example, we can see a soldier. So initially at the starting level, the soldier will have no idea of the player's whereabouts or existence. And so they will not be able to satisfy the kill enemy goal. So instead, it'll fall back onto the patrol goal. Now, it'll patrol the area it is in until it encounters the player, in which case the the kill enemy goal will then be prioritized and the soldier will start to shoot or melee to attack the player and will try to go in or will prioritize killing the enemy. Now we can see within an assassin, they approach this differently based on its actions. So initially, if the player's location is not known, the assassin will cloak itself and run around the area and attach itself to different locations on the wall. Now, when the player is located, the the assassin will jump down and try to attack the player from the wall just using melee actions. So we can see that even from here, the these two different characters will try to satisfy the kill enemy goal in two different ways. The soldier has a gun and a melee weapon and will try to use either in order to attack the player, while the assassin will hide more until the player is encountered, in which case it'll wait till it can get close and then attack the player using melee. The rat is another interesting character because it will patrol the area similar to the previous two examples while the player is not found. But the rat has no way of attacking the enemy, attacking the player, or attacking the enemy in any way. So it has no way of meeting the goal of kill enemy. So because of this, it will fall back onto the patrol and will just keep staying within that. The patrol will keep trying to work to satisfy the patrol goal. So here are some of the main differences between F.E.A.R AI and strips. So while the F.E.A.R AI does resemble strips, it does have some differences that are needed in order for the planning to work in real time, as well as in more of a fast-paced game environment. So F.E.A.R implements a cost per action so that certain plans can be prioritized over others. A* is used to create a graph of states, and the nodes are the states of the world, and we are searching for a plan to the goal state. Edges connecting the different states of the world are the actions which update the world to a new state. A* searches for the lowest cost sequence of actions to complete a goal. So adding and removing delete are lists. So are removing add and delete lists. So F.E.A.R uses a fixed array, which is used to represent the state of the world instead of precondition and effects, such as would be used by strips. So using this fixed array helps the system to run faster, but does come with the downside of only being able to focus on a single target or focus on a single weapon due to the fixed length of the array. Procedural preconditions. Additional preconditions can be checked through the check procedural preconditions function. This allows the system to make conditional checks that might be too cumbersome for the system to consistently keep track of. One example of this is the runaway action for the AI. The system needs to make sure that there exists a location that the AI can safely run to, but keeping track of a safe location will become too taxing on the system to keep track of this at all times. So this system allows the system to only make the check when it is needed. Another example is procedural effects. So in Strips Planner, when an effect happens, it's instantaneous, and this is different to this is different to a game environment where these effects don't always happen instantly and instead will take time. This is where it connects to the finite state machine. When a plan is executed, actions are sequentially activated. This allows the finite state machine to set the current state and any associated parameters. An activate action function sets a state parameter and provides any additional information needed for the state, such as location to move to, cover positions, or a player to shoot at. So these are some of the benefits of using planning. Oh, one last thing I missed within the slide is serialization isn't required for F.E.A.R AI. So strips does require serialization for it to be able to find a plan, but because F.E.A.R does make use of procedural preconditions, this cannot be maintained within F.E.A.R AI, and so this is one of the big differences between the two. All right, let's move into benefits of planning, decoupling actions and goals. In previous methods, if you want to create characters that acted differently, you would need to create branching paths within the finite state machines. This would add more complexity into the system. By utilizing planning, we can simply provide each character with their own set of actions and that are specific to them. This allows the creation of new characters by taking actions from different characters and combining them together to be able to make new action sets. The, the use of working memory allows each goal to have the same information. On the left, you can see that each state is closed off to every other state. This creates the problem where a piece of information, which is valuable to one state, might it might not be able to get that information right away, making the character act in undesirable ways. One example of this, provided by the paper, is a character sitting at a desk would get shot. They would then finish their work animation before standing up and then dying. In this new system, if the character is shot at the desk, they can hunch over and die at the desk like the player expects them to. They don't have to complete their previous action before moving into their next action. The second benefit of this is layering behaviors. So you can get tactical behaviors by layering a variety of simple actions together. With the planning system, you can just toss goals and actions into the system and allow the AI to figure out how to utilize the actions to accomplish its goals. The developers aren't required to specify each transition, making an efficient system for creating complex characters. So one quick example of this is if the AI has the kill enemy goal and the player is far away, they will decide to use range attack to help best accomplish its goal. However, if the player starts shooting back, they will prioritize dodge action to get out of harm's way. This is achieving the dodge goal. If the AI is hit by the player, it will prioritize its life and move to cover, satisfying the cover goal, which will then be its new priority. Now it's in cover and it feels safe, it can start prioritizing the kill enemy again, but it might decide that the best way to accomplish this goal is to blind fire at the player from cover. If the player gets close to the enemy, it will try to accomplish the kill enemy goal by attacking the player using a melee action. As you can see, the AI changes tactic based on the situation. This creates the feeling of complex decision making. Last main benefit is dynamic problem solving. Dynamic problem solving allows with the use of working memory, the AI can take into account failed plans when developing new plans so that the system doesn't get locked into a single plan which continuously doesn't work. Here we have the example where an AI, which is represented by the red circle, is trying to enter into the area where the player is, which is represented by the green circle. But the player is blocking the door with their body, and so the AI can open the door. The AI realizes the initial plan didn't work and notes that the door is blocked by an obstacle. So it decides to enter through the window, which can be seen here by the blue area. So squad behavior is one of the big interesting parts of this paper. Squad behavior comes from the AI being given squad orders that mimic the AI working together. What is actually happening is each AI is working independently, but are following goals such that it looks like teamwork. Within F.E.A.R, there are 4 different goals. Get to cover, which has one or multiple AIs move to a cover location while the rest of the AI provide cover fire. Advanced cover has one or multiple AI move towards the player while the rest provide cover fire. Orderly advance has the AI line up while moving together, having all but the last AI looking forward and searching for the player and covering the rest, while the last AI faces backwards to cover the rear. Search has the AI split into groups of 2 and search for the player. These are steps that are needed to activate squad orders. So the system will find AI that can fill the required slots for the behavior. Orders will be sent to this squad. These orders will be goals for the AI, which can be chosen to follow or not based on the situation the AI is in. If the AI the AI will prioritize following the orders unless something happens where the player maybe throws a grenade at them, in which case it will then decide that running away is then the more desirable option. Um, so once the AI have been given the orders, the system will monitor them and see if the AI succeeds or fails. Squad communication has a very interesting concept to it because it doesn't actually provide any information to the AI, but rather it informs the player that the AI is doing things intentionally. This reminds me of the AI explanations, where the information provided doesn't help the AI, but is rather to inform the human of the reasoning for decisions being done. These communications are programmed to appear only after certain conditions are met, but I still feel it effectively accomplishes the goal of informing the player. Same with complex squad behavior, such as ambushing or flanking. These aren't programmed into the game, but rather come from creative level design and individual AIs working to accomplish their own goals. But it does build the illusion of complex teamwork being done. Some of the strengths and weaknesses I found with this paper. So strengths, I found that this was a great way to approach the problem of overly complex finite state machines. This was an interesting way of utilizing planning in an unconventional way. The purpose are uh, the paper does propose some use cases for planning in other areas of development, such as um, they talked about how instead of the planning just being used for the actions, it can also be used for the communication so that they don't have to predefine where the cases where different communications between the AI will be used. I did find that the communication between the AI was a great way to cue the player into decision making of the AI, and it made the immerse the player more in the feeling by giving them that extra information. Uh, there, they also made great use of the squad formations and having a great illusion that the AI is planning around what the player is doing, but instead it's just individual AIs trying to accomplish their goals. One of the weaknesses I found is currently the AI is only able to focus on one character weapon at a time when planning because of the fixed array, as well as the AI will keep running even when not close to the player, which can be taxing on the system. So if an enemy or a rat at the beginning of the level is left behind and the player gets to end the level, the rat is still following its state machine and making plans. All right, this is one of my questions. Within different approach to planning that could be used within different applications of planning that can be used in other types of games. They mentioned an RPG example where they want AI companions to derive what the player is planning to find so that it can find a spot where they can fit into the plan and assist the player. I was wondering if a regression approach, this type of plan would be useful to help derive different goals from the player without having the full context of what they're doing. So this is being able to use incomplete states and trying to figure out where the AI can fit into this plan because the current plan that they approach is still a forward based approach where the player picks up two different items and goes to a certain location. And so the AI puts that together and says, okay, so if we picked up this and we have this, then that the player more than likely is going to try to accomplish this goal. But I feel working backwards might be able to give the AI more ideas into how it can fit into this type of plan. All right, let's move into paper two, playing a strategy game with knowledge-based reinforcement learning. The team wants to create a AI capable of playing and winning in a strategy game called Pre-Civ, which is very similar to the popular strategy game Civilization, which is an empire builder where the player builds their nation over time and tries to either dominate other nations through force or tries to win a space race to the Alpha Centauri system. They create their AI by combining reinforcement learning and knowledge-based systems and hoping to utilize the strengths of each method. Knowledge-based systems. Knowledge-based systems are make use of human knowledge and experience to automate problems using human reasoning. This system is made up of two main components: knowledge base, which holds a large quantity of human knowledge, which is stored in small fragments, and problem-solving methods. In this case, an inference engine, which consists of algorithms for manipulating the knowledge to solve a given problem. The human knowledge is stored within a semantic graph. This is a graph-based representation of concepts, their properties, and relationships. These node these nodes represent or each node represents a concept which holds properties. Each edge represents relationships between concepts. So an ontology, they use they have to create an ontology. This is what defines the schema for the semantic network. This creates a common vocabulary between the humans and the software agents. These entities represent concepts that are, so this contains entities which represent concepts that are the nodes within the graph. Verbs, which are binary representations, which are the edges between each node. Attributes, properties of the entity that hold values such as string, an integer, or scalar values, or a list of scalar values. So inferences are made within the knowledge-based reinforcement learning. So this is done, or so inferences for knowledge-based reinforcement learning. This is the process of deriving knowledge from a given knowledge base. An inference engine is used to solve problems when conflicts occur within the system, which is something we'll go more into later. The system uses abductive reasoning, meaning that the system allows the semantic network to find possible solutions to the current problem based on the rules provided to the knowledge base. The system verifies these solutions using expert knowledge provided to the system. The system is able to determine which solution is best, which best fits the given scenario. So reinforcement learning. So reinforcement learning, I'm sure as we all know, um, is used to learn an agent's optimal behavior towards predefined goals from the trial and error experience of the agent interacting within their environment. This system uses a model-free system, which utilizes the Monte Carlo method. This method is based on averaging over the sample returns, meaning it averages the values provided from multiple runs or episodes, and uses this to build an understanding of the system. This is an action value function for policy estimation. This means that over a number of episodes, it will begin to build a better understanding of the action outcomes, but it doesn't actually know the actual transition probabilities of these actions. Due to this, it encounters the issue where if state hasn't been visited by an agent, the system has no knowledge of the state or how it can get to it. This system uses a greedy approach, which maximizes the action value for each iteration. This means that it will select the highest estimated action value function at each step. So this is a brief example of how Monte Carlo works. Here within the given example, we are provided 4 episodes. And by following each of the paths within episodes, we can determine the cost of the paths used, or of each of the paths used. Based on these, this is what's being done here. So if we start off in A, it costs 1 to go south, and then to move south again, costs 1, and then we get to the goal state where we get plus 10. This is where we're getting this value where if you start at A, it'll cost you 8 in order to reach the goal state. If you start in C, it'll only cost 9, and if you just start in E, then you will just get the goal. For each of this is done for each of these episodes, and here we can see that based on the number of times that these states appear, we average over their costs based on the number of times that they appear within these episodes. So both times when we started from state A, we were able to get a cost of 8, meaning that for both times you add together, average, and then we get an estimated cost of 8. Now with B, we have 2 times that B is used, but one time B goes from B, C, E, in which case we would get the same value such as going A, C, E. But we can see in episode 2, it follows the path of B, C, D, which D has a negative reward to it, meaning that this will update the values that the estimated values that were used, and we will get more negative numbers. This affects the cost, the estimated value here. And same with C, because this is the primary area where the difference is happening, where if you're in C and you use south, it has a chance of taking you to state E, or it has a chance of taking you to state D. So here we could see that because C is used within every one of these plans, it appears more often than within these other plans. And so we divide this by 4 because it shows up within 4 different plans, and we get an estimated cost of 4. Using this Monte Carlo method, we can also estimate the probability of taking actions within each state. So as we've seen before, if you go from A to C using east or A to C using south, these happen 100% of the times. And well, we always know that these following these so far will take you to the C state. Now, what differs from is in 3 of the 4 episodes, C using the south action will take you to state E. But in one of the episodes, C taking the south action takes you to D. So from the information that we are given, we can determine that A will take you using south, will 100% take you to C. B taking east will 100% take you to C. C taking south will give you 75% chance to go to E, and C taking south can also give you a 25% chance of going to D. These may not be the actual values of the actual percentages, but based on the Monte Carlo method, we're able to estimate these values if they are unknown. So basic rules and multi-expert knowledge. So a knowledge item, which is used to refer to a single rule in the knowledge base. So first is made up of these items: key, which holds information about the rule that is more for the readability of humans and isn't really isn't really helpful to the computer. On holds conditions based on factual knowledge that determine when rules are relevant. When is an additional condition that makes sure that rules are only used at a specific time, even if the on conditions are met. Do is the procedure that needs to be executed when the on and when conditions are met. Basic rules were provided by the team, which just met the basic needs of playing the game, but didn't implement any types of strategies as the developers didn't really know many of the strategies that were used in the game. So they brought in multi-knowledge experts. So this is knowledge gathered from human experts who were able to confidently play the game and win matches against embedded AI within FreeCiv. This expert knowledge provides different strategies to play the game. One issue that did come from this is that because different strategies are used by different players, there was some conflicting pieces of information which did create contradictions. So they set up the problem using fixed maps and starting points. They had 5 different map setups, which each included 2 knowledge-based reinforcement learning agents, as well as 0 to a number of embedded game AI. The maps that they used were the default map, the USA map, small island map, medium islands, and chaos. Here you can see 3 of the 5 maps that were used, and they want to focus on uh, teaching peaceful actions rather than hostility. And the 5 maps that were used to implement or to help teach the AI different or influence different strategies within the AI. So some of the times the 2 knowledge-based reinforcement agents were placed together, and this was meant to have them try to um, incorporate more trading within their strategies. Some of the times the AI was placed far away. The 2 AI agents were placed far away from each other, and each agent was placed near an embedded AI that was naturally more aggressive. This uh, had the AI build up more defenses and focus on being able to actually build up enough defenses so that they can survive the actual game even against more aggressive foes. They ran a tournament phase, which consisted of 550 games played by 2 different knowledge-based, or yeah, which consisted of 550 games played by 2 different knowledge-based reinforcement learning agents, which played on each map, and they provided 1,100 games in total. For each game, both reinforcement learning agents had different knowledge items which were created from expert knowledge. They only used one of the expert knowledges for each of their games at a time. This provided evaluations on how well that expert knowledge did within the actual game itself, and they kept track of different stats such as resource management, the number of rounds it took to win the game, and if the strategy resulted in a win or a loss based on the map. Here at the bottom, you can kind of see that number of turns for each of the that were based on the tournament, based on for each game played. And because each agent was only allowed to use one knowledge item per game, the next step in this would be to combine all the knowledge into one multi-knowledge base. So within this, we did talk about how conflicts did happen between different strategies. So they implemented conflict resolution. Reinforcement was using to handle conflict resolution, where they applied clustering to segment the state space into a finite number of clusters. 33 features were selected, and weights were applied to the features based on the correlation between feature values and win-loss output. Um, some of the some of the features that were weighted highest were game score, population size, and number of learned technologies, both global and national. And these were all gathered through the tournament phase. Um, when they did do the training, the reward for the reinforcement learning was the number of turns it took to finish the game, and with a focus on minimizing the number of rounds to win. So they did have two lose conditions, one where a nation was destroyed during war, and this was penalized heavier because it implied that the nation's defenses weren't sufficient enough to build a last of the game. And so they want to penalize this heavier so that the agent would always uh, build sufficient defenses to build at least last of the game. The other lose condition was another nation reached the Alpha Centauri first, and this was penalized less heavily as it meant that the agent was able to survive throughout the entire game, but just wasn't fast enough and needed more time. Here's conflict resolution continued. So a stochastic policy was used within the system. So while the Monte Carlo method did prioritize or did use a greedy approach, which prioritized the highest action, the stochastic policy here did incorporate some randomness into the system so that different strategies would be used. So here in the figure to the right, we can see how actions were chosen. Three bell plots are determined from the action density functions. The L limit is used, the L limit here is used to find a good cutoff point to determine the best solution. Mean and standard deviation are taken from each action returns based on previous episodes. The L limit is created by subtracting the mean or the max mean from the max standard deviation. Max mean is taken from the highest mean among the actions, and max standard deviation was the accompanying um, standard deviation for the action for both the max mean and the standard deviation. Now that the L limit has been chosen, they use the area under the curve to the right of the L limit to determine the probability for the action being taken. So if the area is larger, there's a higher probability of the action being taken. And if the area is low, there's a lower probability. So you can see that this action has a very high area, um, and then these have lower areas. So that means that this action will have the highest probability of being taken, but there is still a chance that these two actions could be taken. So here in results, we can see that the AI did make use of different strategies at different times. So here you can see that the AI followed this player strategy initially and only having a set number of cities at first, where eventually it starts building up and following these two players. And this player here um, maxes out their cities around 40. And you can see the AI does something similar before reaching a certain point in the game where it decides to start building up again, following more of this player strategy. So at different points in the game, sometimes it's more optimal to have a less number of cities so that you can build up more resources, while later in the game, having more cities is more optimal as it allows you to build higher number of resources and have more control over them. This is another result where we can see a similar trend where this is the population rate over the number of turns. You can see that all strategies just in general um, go to about the same, but up until about turn 150 or so, where um, the strategy stays pretty consistent. But this strategy here, you can see that both where it had a jump in population, you kind of see a similar jump in population here within the AI. and the AI is able to build up a bigger population than any of the other players in a less number of turns. So strengths and weaknesses of this paper. So a tournament phase was a good way to determine the pros and cons of different strategies. The using two AIs within tournament and training helps provide a large number of data based on for the a large number of data considering the length of each game, which they said was about 8 to 12 hours. As Free Civ is a slower strategy game, I feel this system had time to show its strengths. The slower paced strategy game allows the system to pick up on different strategies that can be explored. And weaknesses, training with fixed maps, locations, and nations might make the AI only be able to do well under certain circumstances. The AI was primarily trained to be peaceful, but in cases where other AI or players aren't willing to cooperate, this might introduce issues. This system won't work well in a fast-paced environment such as F.E.A.R, as it needs time to analyze and make decisions. And last questions. Can an AI planning technique from the previous paper be created to play a game like this efficiently? Would a switch to using partial plans instead of state-based planning allow the AI to incorporate some of the human knowledge? Would the expert knowledge provide, and next question would be, would the expert knowledge provided to the reinforcement learning system allow the AI to outperform the planning system due to Free Civ game having multiple strategies for winning? And these are just my final thoughts. And thank you for coming to my presentation.